and welcome back to Precalculus 1 on this glorious Tuesday afternoon.
Hi.
The day before? The world ends. Okay, that's... Oh, season finale. Oh yeah, the election day is today, right? Yeah. All day. I see how it goes. Okay. So, what happened?
You lost one.
Oh, you had to go to work. I understand. What I was talking about? Oh yes. So let's first think a little bit. This is a jar. It's a nice jar, right?
Very nice jar.
And what I'm going to do is I'm going to put a single bacteria on the bottom. A single bacteria. And now what happens is every minute bacteria splits in two. That's how bacteria multiplies, right? There's no dinners and stuff, nothing like that. It just splits into half and you have two. And then the others will split and so on. Now, it will take 12 hours for this jar to be completely filled with bacteria. So every minute bacteria splits in half. We start with one, there it is on the bottom, and every minute bacteria will split into two. It will take 12 hours, so jar is that large. It will take 12 hours for this bacteria to fill the jar. My question is, at what time the jar is halfway full? At what time the jar is halfway full?
Question: the bacteria that already split, and they split again?
Yeah, they keep splitting because they have to split, right? If you split only once in a minute, then you will have just two, and that would not fill, right? Because it would be just two spots on the... So at what time we are going to have a half of the jar filled with bacteria? Come on, say it. 6 hours? That's what I heard 3 times so far. 8 hours, 10 hours. At 11? 11 hours? So now I have 6, 8, 9, 10, 11. You go with 10. What happened?
I agree with 11.
You agree with 11?
Yeah.
It's like a Price is Right. Anyone wants to bet $1? Okay. So now let's learn about the exponential growth. So you start with one bacteria, and that splits into 2. And then each one of these splits in 2. So this is at time 0. This is 1 minute later. This is 2 minutes later. Then each one of these would split. 3 minutes later, you have 8 bacteria, and so on. The jar is halfway full. Remember, if each bacteria splits into 2 every minute, work it backwards. 11:59, exactly. Halfway full, 11:59. Because, guys, when all of this is filled with bacteria, every single one is going to split into 2, which means, right? It's going to fill the other half immediately. So this is how the exponential growth happens. We have the issue, burning issue, that is not addressed almost at all, of population on the Earth. Depending on which school of thought you look at, the carrying capacity of the planet is anywhere between 10 billion to 15 billion, depending on which mathematical model you would look at. What does that mean? 10 carrying capacity and 10 billion and 15 billion. How much planet, yes, how much people we can actually have on the planet. Because if you look at the population, right, everyone is using resources in terms of the energy. We're charging the phones, we're using the gas, right, to get places, using electricity in all different ways. And the resources on the planet in terms of minerals and everything else are finite. Also the space, because we don't live generally in deserts, in oceans and things like that, right? So thinking about the livable space, right? So looking at that and the fact that we are at 7.4 billion right now, we might be running out of space for new incoming people very quickly. Now, on top of the fact that immortality is being researched already, and that will be effectively printing organs or anything that is wrong with us and actually replacing it, just like car parts or computer parts, fairly quickly. So thinking about those kind of things, do you think that this bacteria at 1159 would solve their problem of population by getting another jar, equivalently another planet for us?
No.
Hell no, right? Because if the jar is full at 12, at what time is the second jar full? 12:01. You see this jar over here that is empty? It's full at 12:01. Because if this jar is full at 12 and each bacteria splits in half, the second jar is full at 12:01. And how many jars at 12:02? 4 jars. At 12:02, 4 jars. The more people, right? The more bacteria, the more splitting. Actually, we don't get to split people. What happened? No, it takes about 9 months to cook up a baby. I don't know if you know. It's not as easy as bacteria. Yeah. So we have this as the exponential growth. So now that we are trying to understand how the exponential growth works, we can model this mathematically. And for this issue, we can use 2 to the x. Y equals 2 to the x. So think about this. At time t equals 0 minutes, you have 2 to the 0, which is exactly 1 bacteria where we start. T equals to 1, that's 1 minute later. It's 2 to the 1, it's 2, which is 1 bacteria split into the 2 bacteria that we have now 1 minute later. At 2 minutes, it's 2 squared, right? Because that's our exponent, 2 to the t. And that's 4, which makes sense because each of the bacteria there split into 2, so you get 4. And you had the diagram earlier. For 3 minutes, that's 2 cubed, which is 8, and so on. 16, 32, 64, 128, 256, 5, 12, 10, 24, right? 2048, and it goes on and on and on. So it grows quickly. there is a graph for this. So now I'm going to write in the general term y equals a to the x, known as exponential function. A is called the base, x is called the exponent, and then this exponential function will have properties. So what do we have as properties? Well, first of all, let's figure out a graph for exponential function. So how about we take a look at this example, y equals 2 to the x. Let's start there. And then try to get a general idea, right, for the shape. One, two, three, and 4 I can't already fit. Let's get some negative values in as well. We're going to do the middle school method. -3, -2, -1, 0, 1, 2, 3, 4. And we are choosing x's and computing y's. So how much is 2 to the -3? One over 8. So 2 to the -3 has to be written as 1 over 2 cubed. 2 times 2 times 2 is 8, so 1 over 8. How about -2? Anyone? 1 over 4, a quarter. How about -1? 1/2. 0, 1. And then 2, 4, 8, 16. Let's graph these points. So I have 0 and 1, and then 1 and 2, and then 3 and 8, and then I have 16 on the 4, 8, 9, 10, 11, 12, 13, 14. 16 all the way up there. Then I have a half, a quarter, and 8. So there it is, exponential function, and it goes through the y-intercept of 0, 1. So now these are some properties of exponential functions. Y equals a to the x. We say x-intercept, none, unless you move it. Obviously, if you move it, you can create one. Move it 2 units down or 1 unit down, doesn't matter. You will immediately create one x-intercept. So x-intercept, but in default state, x-intercept none. Y-intercept is generally at 0, 1. How about domain? Very good. All real numbers, so you can put either double bar r or -infinity to infinity. How about range? 0 to infinity. What kind of, am I using bracket or a brace or a parenthesis for a 0? Parenthesis, yes. Because the graph never touches 0. Okay, we have that. Great. And now we're going to have the end behavior. So on the side, I'm going to draw a general shape like this, going through 1. And I'm going to say growth, and then this shape, call it decay. So if you know your 1/6 very well, what's different between these two graphs? What kind of transformation happened? Flip on y-axis. And how do we achieve that, the flip on y-axis? Negative. Where? I'm like a little kid.
The y was in the exponent, wasn't it?
So which one you make negative? X. Good. So this one over here would be y equal a to the x, and this one would be y equal a to the negative x. Now this is the knowledge of 1.6. Technically I was not supposed to draw this, right? Because you are supposed to figure this out like this, because you know 1.6, if it's flipped on the y-axis, negative x is around. But since I am the nicest person you know in your lifetime, I did it. And you're welcome. Just few rules so we don't get into trouble. When you say y equals 2 to the negative x and y equals 1/2 to the x, it's the same thing because of the basic rules of exponents. Are we all agreeing on this?
Yeah.
This is basic algebra, which allows you to, with the negative sign, to flip the fraction. Both of these obviously decay, right? Because you have a negative x. So decay can be hidden, right, through a fraction if the fraction is less than 1. So on your calculators, whether you're using the graphing one or the scientific ones, again, no graphing calculators on the exam, you are going to have the little caret, right, like that, button, which is the exponent button. So you're able to actually graph these functions when you go into, on the graphing calculator, right, you can go into the graph screen and then type in the equation using this as the, so it will be y equals 2 caret x, and that's actually 2 to the x, and you can get the graph for it. That's the calculator portion. Now the next question is, how precise could you possibly be to draw these? And the answer is not that precise, especially if you're not using graph paper. You saw how tedious was to graph this, and then even for x equals 3, which went all the way, for x equals 4, which went all the way to 16, these functions grow very quickly, and you run out of space to graph them very fast. But that doesn't mean that we can differentiate between multiple graphs. So this is your standard, let's say 2 to the x. And what's going to happen with Larger value is going to go in and grow faster. So let's say 3 to the x. And then the next one is going to go even faster, 4 to the x. So it's not humanly possible, right, if you really try, right, it's not humanly possible to draw these to the greatest precision. So generally, we will just go and say, yep, there you go, done, right? We know it goes through 1, and we move along. If you have 2 of them to graph, then clearly something over there has to happen in terms of that the ones that have higher base are closer to y-axis because they rise faster, right? So they have to be more on the inside. So now, well, this is graphing. And now I want to do more advanced graphing. So exponential functions are functions. And since they are functions, we can shift them. Use 1.6. That section never goes away. Anytime you learn a new function, which is now exponential logarithmic, then the next course, 6 trigonometric functions. Then you go into calculus with hyperbolic functions. 1.6, 1.7, 1.8 are obeyed by all functions under the sky. All right? So, how do I graph y equals 2 to the, let's say, negative x, let's go with positive x. So let's go with x minus 3 and then everything plus 1. Right? So you're looking at this and you know you have to use 1.6 transformations to graph this. Where do we begin? Yes.
You want me to tell you?
No, sing it.
All right. So first you shift it up 1.
Okay.
And then it goes to the right first.
Great. Oh, that's great. Perfect. I forgot one of the most important things over here. I'll write it in blood. Vertical asymptote. Sorry, no vertical, horizontal. At y equals 0. Horizontal asymptote at y equals 0.
Every time?
Well, not now, in this problem, because it's plus 1, so everything goes up by 1. So default case has the horizontal asymptote at 0. This case is going to have it at 1 because everything goes up by 1. So asymptote goes up by 1 as well. And that's where we start. So you want to graph this. We start with default case that goes through 1, right? So this is just 2 to the x. The next iteration is shift everything 1 unit up. So your good old y-intercept of 1 becomes 2, and your asymptote moves from x-axis, which is y equals 0, up to y equals 1. And you draw the same exponential function through 2 now. So this will be 2 to the x plus 1. And the final step is to shift everything where? How many units? 3 units to the right. Great. So I still have the horizontal asymptote. And now this point that used to be at the y-axis is going to go 3 units to the right. And we draw the same shape through this. You have to label this as 3, 2 for full credit. I mean, if you don't want full credit, don't worry about it. And that solves the problem. We shifted everything 1 unit up, and we shifted everything 3 units to the right. So try one on your own. Y equals 3 to the negative x plus 2. Done? Awesome. How many transformations do we have?
2.
2 transformations. Very good. What are the 2 transformations?
Y reflection and up 3. 2. Up 2. Up 2.
Up 2. Run, man. All right. You okay?
Yeah.
So we start with the default picture. That's 3 to the x, right? The graph. Then we are going to say reflect first, which is now 3 to the negative x. And then we're going to raise everything 2 units up. So the asymptote will go up. That's the asymptote. And the y-intercept as well. And we draw the same shape, x and a y. And this is our 3 negative x plus 2.
So I'm just confused. Like I did that, but like as I'm thinking about it. So like the
Used to be at 0. 0 plus 2 is 2. Y-intercept used to be at 1.
I'm supposed to move it up
2.
from that?
2 from 0. Used to be at 0.
Do you
And
flip it first, or do you
always reflect first.
always reflect first?
Always reflect first, because certain cases might be trouble.
All right, thank you.
You're welcome. All right. Let's do one more, since you are so nice. Let's this is going to have multiple transformations. So let's go with
Why?
all right. Everyone except Holly, let's go. 3. It really doesn't matter which number I pick. So I'm picking 5, negative x minus 3 plus 1. Let's do minus 1.
Great.
Yeah, just because some of you are writing with pens, so it's always fun to switch. There is absolutely no other reason. Yes.
Yeah. Now I'm lost.
All right, so let's see.
Wait.
No,
Question.
So it goes to the left.
Yeah. have negative x minus 3, which means that when we factor out that minus to use for reflection, it ends up being x plus 3, which means the whole thing goes to the left. Exactly. So if you drew it to the right, it's time to, if you use pen, rip on the page, and then start all over again. So I'm just going to go and do this first. So now we start with default, going through 1, and then reflect, going through 1, and then maybe shift down. So now it goes through 0, 0. And then finally, 3 units left. It goes through negative 3. And that will be it. Now, let's say you want to check this, right? You're interested if this is actually good. You can pick this point here, because you will always have one point that makes sense from somewhere, which is x is negative 3, and plug it in. Negative 3 plus 3 is 0. Negative 0 is still 0. 5 to the 0 is 1. 1 minus 1 is 0. Y coordinate for this point is 0. It's good. If it was anywhere else, it would not be good. If this was on the other side, it would go through positive 3. Then 3 plus 3 would be 6. And then you have 5 to the negative 6 minus 1 would not give you 0. So you can check. Once you draw the final stage, you will have this point, which was the original y-intercept, somewhere. And you can use that x-coordinate to figure out where the y-coordinate is to check if your transformation was good. You can also say minus 3 right here. Minus 3 is plus 3. 3 minus 3 is 0. 5 to the 0 is 1. 1 minus 1 is 0. So it works. All right. The next part is figuring out ready? Next part is figuring out the word problems with these exponential functions. And one part that we really use this for instance, would be finances. So let's talk about, say, a car loan. You can also think of the student loan or something else. Not the mortgage, though. Mortgages are a little bit more complicated. So we are going to use the formula where the amount you owe is principal times 1 plus r over n to the nt. Clearly, this is exponential function because you have some kind of a number over here raised to the t, which is the exponent. And this is the formula that you will have to know. It's a very useful formula, by the way. So now, the A is the amount, P is the principal, R is the rate. You want to have that as a decimal, but the rate is usually given as a percent, so you convert that. And then time, usually in years.
What's the N?
N is the number of compounds. Yes. Which is payments per year. Actually, it is a calculation that adds interest. We talked about interest at one point or not. Interest is what? What is interest? I'm sorry? No, that's the no. What is the meaning of interest? What is it?
It's like when like you're borrowing money.
Okay.
So for the time that you're borrowing, they tack on interest. The money that.
But what is interest? Everything you said is correct, but it doesn't answer my question.
Money that the borrower earns as a.
That's principal. The money that I borrow and I have to return. That's principal. What's interest?
Basically, the service fee for allowing you to take money.
I'm sorry?
Like the service fee.
That's it. Thank you. It is a service fee. You guys go to the mechanic, and the mechanic charges you service fee for changing a part. Charges the part, right? So if you go and change a battery, right? It says, okay, battery is $100, but then the work is another, I don't know, 40. So that is the $40 is the service that mechanic provided. You go to a hotel to rent a room, they say 80 per night. It's the service. You go leave a tip at a restaurant, right? You pay for the food, I hope, right? And then you also leave a tip. So that tip is the service money. So interest is the service money because someone, whether it's individual or the bank, is giving you the loan. You need the loan because you don't have money to give up front for the car, for the school, for something, right? So you take the loan and then you pay it over time. The extra money that it's put on top of what you owe is called interest, and that is the service you are paying back because no one is going to lend you money for free, right? It's a service. So N, which is the number of compounds, is how many payments you are making, which is where this interest calculation happens. So if you are paying off a credit card, paying off a car, paying off something on a monthly basis, they compute interest on what the amount you have still to return, right? So now, let's take a look at the example for all of this. What's the price on the car? $20,000, okay. Do you have any down payment? $5,000. Is the credit score good or bad for the rate? Bad. So what's the credit score? Let's say it's good credit score. We get 3%. All right, that's fine. Whatever, 3%.
It's not even under. That's under. Make it 3.25 because that's under the minimum.
Yeah.
3.25 right now.
Per request, we are changing the percent to be 3.25. And
Prime.
on
It's under prime.
on how many years you want to take this loan? 3 years,
4.
5 years? No, 3, 5. Shh, guys, 3, 5, 6, 7. That's what's offered. 5 years. Let's take a look at the monthly payment because we can compute everything from here. So first of all, we're also going to make this problem a little bit richer, right? So let's include a tax 7% because you have to do that, right? And then plus you have the title, registration, all of these miscellaneous fees.
Title
at the dealership. So how much would that total, let's say? $600? Okay. For miscellaneous cost. There we go. All right, so let's start. We are going to take $20,000, multiply that by 1.07 for the tax.
What? Why is it 1.0?
1 will keep the $20,000, and 0.7 is a 7% extra on top of it for the tax purposes. So what we are going to have here is $21,400. We are going to subtract $5,000 down payment for a total of $16,400. And we are going to add, oh, look at that, how convenient, $600 for miscellaneous cost. So we have to finance $17,000. So we have to finance $17,000. Now that is your principal. So what's the amount that you owe at the end? It is the principal, which is $17,000. 1 plus the rate at which you are borrowing is 0.0325. If that was a sneeze, bless you. Divided by n, how many payments do you have in a year? 12. Raised to 12 times 5, which is n times t, right, over 5 years.
Why do you make the decimal so long? I would think it was
Because you,
0. Oh, no, no.
right, 0.3 would be 30%. So now we're going to compute in parentheses 1 plus 0.0325 divided by 12 is going to give us 1.0027 and then 0.8 blah blah blah. Well, actually no, let's put 0.8 because it's 4 decimal precision, raised to 60, which is 17,000 times, so this number raised to 60 is 1.1762. Guys, 4 decimals precision, okay? Error accumulates very fast with exponential functions if you cut them off on a single digit or a 2-digit. Keep 4 digits, 4 decimal places. And then that times 17,000 gives me $19,995.23. Monthly payment,
I got 4.
well, it's wrong.
No, like 19,995.4.
Well, that depends on how you round. It's good enough.
No, but that's what I got with the decimal that you put in there, 120.1762.
Yeah, you probably calculate on Apple phone, and that's fine.
Bye.
We're dividing the number that we have to, number that we owe with 60 to get 333 and 25 cents per month. So you want to buy a $20,000 car with $5,000 down payment with all of this, what else? The 3.25% over 5 years. Your monthly payment is $333.
That's a lot of money.
So for a $20,000 car, right, after $5,000 down payment. Now these are real numbers. These are real numbers. So you might have to take, right, 20,000 to finish Rutgers on same condition, right? 20,000 will get you through what, 2 years? Or if there's no tax and stuff like that. But technically, once you graduate 6 months after, right, the loan kicks in because they give you a grace period of 6 months to find a job and start making money and so on. So these are the things this is how loans work. And you can do this calculation. Now you will have to memorize the formula. It's called compound interest. Write it down, compound interest, because that compounding, the n, right, compounding, can happen once a year, twice a year, 4 times a year, like quarterly, or monthly. Can also happen daily, right? 365 days in a year, so daily. In which case n is 365. If you have the monthly, it's 12. If you have annually, n is equal to 1. Quarterly, n is equal to 4, right? 4 times a year. But monthly is most of the time 12, right? That's most of the time. One more concept left in this lecture, and that concept is the idea of continuous compounding, for which we have to learn the very special function called natural exponential function, whose base is the irrational number e. E, in honor of one of the gods of mathematics, Leonhard Euler, who was the first to figure that out and put some mathematics around it. Well, some mathematics, a lot of mathematics around it. So, natural exponential base e. So e is approximately 2.7182818227, and actually goes on forever. You can find that value on your calculator by simply pressing E and then enter on your scientific calculators. It's going to be somewhere in the right column for TI-8384. We have the natural logarithmic function written as y equals e to the x, whose features are identical to everything that we did earlier. Same xy intercepts, asymptotes, same everything, same graphs. It's just that it's a very special number. This is the one that occurs in nature. So as we do our problems, 90% of the time you will be working with base E, and then 10% of the time you will be working with other bases. Now, this number is actually defined in calculus using a calculus concept of a limit, and I will write down what this number is. You're not expected to understand this or memorize it. You will have to once you're in Calc 1, but not now. So E is equal to the limit as n goes to infinity of 1 plus 1 over n raised to the n. So this is the actually definition this is the definition for number E. And there are calculations and so on. There are other definitions as well. Another one learned in Calculus 2 and so on. So the value is somewhere about 2.7. So between number 2 and 3, right? And we have this form here as y equal e to the x as the base form. So you can literally think about this as 2.7 to the x, right? Where actually it's not 2.7, it's infinitely many decimals that never repeat. It's an irrational number. It cannot be represented as a fraction. Now, what this does gives us this what we call continuous compounding, which will actually put the limit up to the highest value, right, that you actually can pay for the car that we discussed before. You see, if there is a compounding only once per year, you will be paying less than 333 per month. If you're paying once per year, you are making only 5 payments in 5 years. And the interest calculation will happen only 5 times, which means less interest is collected, which means the lower payments. But we pay monthly. If you are to go and pay every day, you would pay probably, you will definitely pay higher amount than 333 because calculations for interest happen more frequently. They happen about 30 times a month rather than once a month. So if you want to calculate absolutely highest payment, you can use the continuous compounding formula, which is given by amount owed is the principal e to the RT and for continuous compounding on the same numbers as before, we have that the principal was exactly 17,000. We have that the rate was 0.0325, and we also have that the time was 5 years. You can just plug this in the formula and compute the value. And we get what? Well, let's compute. 17,000 times E, and then these two have to go in a parenthesis. No, just the exponent. MPT is the monthly payment. And you can see that it is only 7 cents more per payment. But 7 cents times, right, 60 payments is how much?
Like $6.
40 bucks. Like 42 bucks.
$36.
7 times 6?
6 times 6.
No,
7
7.
times 6.
7. So $4.24. All right. So with the continuous compounding, you put the largest possible value. The graph and everything else, as I said, looks the same as 2 to the x, 3 to the x, and so on. Most of the formulas that are there in physics, engineering, business, and so on are going to be with E as a base, natural base. There are certain formulas in physics that are using base 10, right? And we'll talk about some of those, but E is one of the most important ones, and it shows up everywhere. So we'll be using E most of the time. 2 class preps for next class. All right, let me just shut off the stream, by stream.